Before you get started today, day 5, I suggest reviewing the terminology from last week and make sure that you're really comfortable with it. It will make this lecture and all future lectures much easier to understand if you just take a minute and go back and look at the last periods or the previous days, I should say, lecture. Also, if you can take a moment and reacquaint yourself with, remember we did the advantage red, the red uniforms versus blue uniforms. Reread the question or the research question, excuse me, and make sure that you understand it. So remember, we were investigating whether random chance alone, so whether it was just random chance, is a reasonable explanation for this result that red won more often than blue. Or did the data actually provide some evidence that red tends to win more often than blue in these kind of matches? So once again, we can't talk about large team sports because we're looking at individual combat sports. So it's always important to look at what the research question is and what the study looked at before you draw any conclusions. Previously, we used the one proportion applet to calculate the p-value, so I'm looking right here, the probability that there could be 248 or more wins in a sample of 457 matches by chance alone, and found the p-value to be, I put 4.2% based on this, but actually, if you look back on page 17, you're going to notice that it's actually 4.1%. So if you go back to page 17 in the notes, you're going to see that there is the null distribution that we generated. Now, when I did this problem, when I came back and did it quickly, I generated a new null distribution. So remember, we talked about it. Each time we pull, we're doing 1,000 repetitions of the 457 matches, the heads or tails kind of repetitions to see what happens. So each of these dots represents one set of 457 matches. We did this 1,000 times. So there are 1,000 dots within this. This time when I did when I generated the null distribution, excuse me, I ended up with 4.2% that were as extreme as or more than 248 wins. Wins being heads in this case, because remember we're simulating what's going on. So each time you do this, when you do this at home on your own, your number may be a little bit different. You may get 3.9% or 4.3% or 4% for your actual p-value, because remember, this is our p-value here. And that's okay, because this is going to be a little bit different each time we hit reset on the applet and we generate it. Because remember, these are random, all right? So we found that we have a reasonably small p-value gives us evidence against random chance alone. Just want to reiterate here, because this is only the second week, and I want to make sure we're comfortable that this is supposing that just random chance, when we did this 1,000 repetitions and counted the number of heads, which represented success here, how many times did they come out as 248 or more or higher? And it only happened a total of 42 times. So that doesn't happen very often. So that's giving us evidence that blue does tend to win more because it's an unusual observation. Now, if it had fallen back in here, let's say right around here, I know I have lots of arrows, I apologize, we would have said, oh, that's to be expected. Now, remember, we can't find support for random chance, but we can find evidence against, well, we can't find, let me rephrase that. We can not find evidence that the alternate hypothesis is, that there's any support for it. So to recap, when you have a reasonably small p-value, remember that's found by counting these and dividing by the total number. Sorry, my screen went blank and I panicked there for a moment. It does this calculation for you automatically in the applet. When you have a reasonably small p-value, There's evidence against that it's just random, because remember, our null hypothesis is saying it's just random chance that it's happening. We have evidence that red tends to win more often than blue in such matches than is reasonable to happen by random chance alone. Remember, if it was random chance alone, it would probably be somewhere in here, but we're observing 248 wins, and we also look at any other extreme. So if there was a lot in this tail, if this tail looked more like this here, there was a ton, then we wouldn't find much evidence. If you're still struggling with that concept, I suggest going back and rewatching a video and just make sure you really understand it. Just a quick aside, these first 2 weeks in a lot of ways are probably going to be the toughest 2 weeks of the quarter. And I'll reiterate that in the welcome video, but I just want to say that getting all of this terminology down and getting down some of the key ideas, this is the time to do it. This in a lot of ways, like I said, is the hardest part of the quarter. Hang in there, rewatch videos, come to office hours, ask me questions. That's what I'm here for. Okay. So continuing on with the notes, the next page. What if we change the horizontal axis to proportion of heads instead of number of heads? So if I go back up here, we have the number of heads that have come up. If we do proportion of heads, all I did was I clicked this. Oops, sorry, my iPad fell obviously. I clicked this button. This changed and was auto-calculated for me. Okay, so it automatically calculated that. In other words, remember our p hat was 0.543. I would just leave it as it came up. It's a little more precise at 0.5427. But if you plugged it in 0.543, that would be fine too. But if you already had heads in, you click this proportion of heads, it's automatically going to change this for you. So I didn't have to put anything in there. This, remember, is telling us how many, so this is a count. So how many times it occurred. When those 1,000 matches, how many times or with 1,000 flips, how many times did it come up heads? When I look at this now, did anything actually change? Well, my mean, let's see, my mean here is 0.5. Did that change? Well, yes. And so did my standard deviation if you look at them. If you think about it though, that makes total sense because we're going from a count to a proportion. All right, so remember when we considered what would we expect the mean of the null distribution to be? Let's think about this, talk it through. When we came up with the null hypothesis, we said that nothing interesting is happening. It's just 50-50, so 0.5. Ooh, that kind of makes sense then. So when I auto-generate this null distribution, all of these dots in here, all these dots, I would expect it to center around 0.5. Now, this is a little odd. Am I going to get exactly 0.5 every time I pull the null distribution with an applet, do this simulation? No, you could have 0.49, 0.51. Those are all okay. They're close to the 0.5, that halfway mark. The standard deviation, of course, is now going to be reflected. That variance, it wouldn't make sense for it to be 11 because, well, we can't even go over 1, right? Because this is looking at proportions. So obviously, that's going to be automatically calculated for you. So don't worry, you do not have to do that calculation in this class. But what didn't change? The thing that didn't change at all was the p-value. It is still 0.042. So this did not change, right? Because remember, all we're doing is changing, let's see, that did not change. We're changing how we display the information, but you notice they're still the same. If you counted them, they're still the same, 42 of them out of the 1,000. So note here, the p-value, when you make that change between proportion of heads and number of heads, the p-value stays the same. The interpretation of the p-value therefore stays the same. We're going to say the same thing. The conclusion for the study stays the same. That makes sense because we haven't changed any of the information except what we're looking at. In this case, we're looking at proportion. And we already talked about why does the center, because that's the parameter we expect to be 0.5, random chance. Yes. Does it make sense? Yes, we talked about it. Random chance is 50-50. Therefore, half the time. Moving on. So we have this p-value. At this point, the only way we can generate the p-value is with the applet. So we generate the p-value. It does the counting for us. So that's really nice. But is there anything else that we can use to look at, to make some determination, to look at the measure of the strength of evidence? So besides the p-value, there's another way. And it once again looks at how surprising the observer. So where is it relative to the center is how I think about it. So this standardized statistic, this is specifically, in this case, we're using Z, and this is for proportions. So when we're looking at p hat. The standardized statistic Z is the statistic, in this case, p hat, minus the mean of the null distribution. Well, the mean is going to be that pi, where when we came up with the null hypothesis, over the standard deviation of the null hypothesis, of the null distribution, excuse me. And that's going to be given by the applet or given by me. You once again do not have to actually calculate that. So when I look at this z-score, what is it going to tell me? So remember, standard deviation is a measure of how far from the center we are. This, you're going to notice, if you want to pause and write this down, this z-score gives us a number, a standardized number, because it takes into account the difference between p hat and the null hypothesis value, and we divide it by the standard deviation. So it's going to take into account the variability already. And it tells us how far out or how far away is the observed statistic from the center, and the center being where h sub 0 is, in other words, our null hypothesis. So when we did this, this is once again using that same one that I generated earlier, the null distribution. You always want to make sure you check summary statistics so that you get the mean and the standard deviation, and they're calculated for you. When I go to calculate this z-value, I'd like you to pause and see if you can come up with it and then check it compared to my number. So hopefully you took p hat minus pi over the standard deviation of the null distribution that's given to you right up here. If you do that calculation, always feel free in this case to use a calculator, remember, in this class. Just subtract, divide, and you end up with 1.79. But now we have to interpret, see what this tells us. Okay, pause and take a moment, read what I wrote, write it in your notes, and then come back. So it looked at the interpretation of the standardized statistic. And what we found is the observed proportion of wins, 0.543, in the sample of 457 matches is 1.79 standard deviations above 0.5, which is what the null hypothesis states as the value of pi, which is the parameter. We haven't come to a conclusion yet, but we're just stating the information that we found. Before I move on, let's just think, can this value of z be negative? Well, yeah, if you think about it here, if this is about the center, could I be, let's say, down in here? Would this value, That's going negative, right? And this way we're going positive for how many standard deviations when we look at that z-score. Okay. So now 1.79, what does that tell us though? So there are guidelines for evaluating the strength of evidence from standardized statistics. If you're between negative 1.5 and 1.5, your z-score, in other words, your standard deviations, away from the center, there's not much evidence against the null hypothesis. Can we ever say there's evidence for the null? No, we can't find evidence for that being random chance, because honestly, there are a lot of other explanations that could be possible. Not that it's random, but that we just didn't test the one that it happens to be. You also can, now if you're, let's say, negative 1.7, well, then you're above this, you're going to look at this next one. We always want to be conservative. So negative 1.7 is between negative 1.5 and negative 2. So we would look here, for example, at negative 1.7. We have moderate evidence against the null hypothesis. So not strong evidence, but it's still good. An example here, what about 2.1 or 2.2? Now we can say we have strong evidence against the null hypothesis. If you're negative 3 or above those numbers, so let's say negative 4 or negative 3.5, you have very strong evidence that it's an unusual occurrence. It's an unusual observation. So these standardized statistics will tell you the same things. We're going to talk more about this as we go along, but the numbers are going to be different. And we'll make sure we pull that all together in just a moment. Now, completing the advantage example. I'm going to pause this, I'm going to write it out and come back and talk with you about it. So I'll be right back. Okay, and I probably didn't need to tell you that I was pausing to record because you don't know. Sorry, coming back. If I'm asking for a conclusion on an exam or something, I will make it clear. I will somehow let you know that you need to pull it all together. In this case, it says, does the standardized statistic provide evidence against random chance explanation and provide evidence to say that in general, red uniforms tend to win more than half the time? So when you see something like in general, that's generally asking, it's asking you to have a conclusion, to say something about what you found. So we're going to come up with like a standard, I don't want to say standardized format, but it kind of is, on how to draw conclusions, and that'll come in a future lecture. But for right now, what we want to do is state what we found based on a z-score, of 1.79. We want to say what that means. We have moderate evidence that in general, in such competitions, red uniforms tend to win more than half the time compared to blue uniforms. So we state our value, we state what it means, and then we put it in the context of the study, of the research question, It's important to give the context. If you don't, people can draw some really, let's go with interesting conclusions. So I'm saying in such competitions, red uniforms tend to win more than half the time compared to blue uniforms. Can we say anything red compared to black uniforms or brown uniforms or purple uniforms? No, we looked at blue uniforms. Can we talk about team sports? No, our research was based on that combat style, one-on-one competitions. So we can't generalize to football or tennis. Could we do future studies? Sure, but we can't generalize this to other things. And that's where a lot of times you'll see in the news or in a health magazine where someone will grab a study like this and then generalize and say, red uniforms win the most. Well, you can't just say that, okay? Before we start part 3, which is a little bit different, I want to summarize where we're at. So I'm going to say here, before we start 3, let's look at our p-values and the z-score related. Related not in the sense of uh, you can calculate one directly from the other, but do they move the same way? How do they work? I suggest pausing and writing down what I have here. They are related in the sense of as p-values go down, z-scores go up. It's kind of go, wait a minute, should they both go down or up? No. Remember, small p-values means those counts of how many, when we go back, I'm going to zoom up here. So hopefully you have that written down. When we give a p-value, remember, we are counting how many of those repetitions is what they're called. When we run each of these dots is a repetition. Remember, we have 1,000 of them because we ran it 1,000 times. There are only 42 out of 1,000. So that's a small number. That's our p-value. So p-value is small. That makes sense. Oops, I'm sorry. I would zip right by it. Now, when we have a small p-value, we have stronger evidence for the alternate hypothesis. Now, my z-score, on the other hand, is going to go up because remember, z-score measures how far away we are from the center. So the further we are from the center, in other words, that the value of the parameter, when we do the null hypothesis, we have stronger evidence for the alternate. So once again, going back up here, we're further away, right? We have our z value is higher. So they are actually, as one goes down, the other goes up, and vice versa. Hopefully that makes sense. If not, take a minute before you move on, rewatch a little bit and see. This is an important concept to understand as we move along. So what affects the p-value and the z-score as we go when things change? Recall this research we did on Sarah, the chimpanzee. Out of the 8 problems, she picked the correct answer 7 times. So her proportion for correct was 7 out of 8, which is 0.875. Now, let's suppose that instead of 7 correct, she only got 6. How would that change our p-score and p-value and z-score? We're going to investigate it using the one proportion applet. You can look at mine and then try your own. This is not something you have to turn in, but I do suggest doing it on your own also, just to make sure you're comfortable with these. Here are my results. Now, if let's just say, ignoring the question for the moment, each time, remember, you do it, are you going to come up with exactly the same things that I have? No, of course not, because remember, the null distribution is going to be, well, it will be a little bit different. Should in general it be centered near 0.5? Yes, because remember, that is our null, what we defined our parameter to be, our null distribution to be right at the center, 50-50, 0.5. So before we start looking at these distributions, let's go down to the bottom. The scenario is what we originally started with, that there were 7 correct. The sample size is 8. That's that n is 8. The p-hat we can calculate ourselves. Either she got 7 out of 8 right or 6 out of 8 right. Of course, I'm always using my calculator. Use your calculator. It's good. I used my new distribution here. My new null distribution, I should say, when I did this. It may be a little bit different than when we did the original, because remember, each time we generate that null, it'll be a little bit different. So in this case, I'm going to first look at, let's see, I've got 0.875, so, oh, this must be my 7 correct. And that gives me I have 50-50 chance. Remember, that's the probability of heads or the probability of success. The number of tosses is our n. We do 8 tosses, and we're going to do that 1,000 times. It'd be really hard to do by hand, so we have these applets to do it. Once again, I check summary statistics. I come out with a mean of 0.498. That's close to 0.5. Not exactly, but that's okay. Remember that we're talking over the long run, that it would be your long run proportion. In other words, your pi would be 0.5. So when it did this, I said, well, I want it as extreme, so I did it by proportion instead of by count, and I wanted it looking at 7 correct at 0.875. When it did this count for me, remember it does the count, it came out with 0.280. So there's my p-value. And there it is out here. Now, thinking about it before I move up further, and of course, just popped out that z-score. I'm looking at this without even moving. Would I expect my p-value for 6 correct to go up or to go down? Think about that for a moment. Okay, hopefully you thought about it for a moment. Remember, we're looking at 0.75 or greater. Well, 0.75 is right here, right? So are there more observations? Yes. So going up here, we're going to notice that this is extreme as 0.75. So this is the 6 correct. It's all the same input. I actually didn't change. You notice that the summary statistics didn't change at all. All I did was change this number here. All right, left everything else the same. I just changed this so it would give me the new count. Wow, there's quite a bit more in the tail, isn't there? Which makes sense because we are only saying she got 6. What if I said she got 5 correct? What would be 5 out of 8? Ooh, if it was 5 out of 8, we would be looking at all of this. Would that give us a much larger p-value? Yes. So my p-value now is approximately, for the 6, 0.140. So as my p-value went up, what do we expect to happen with our z-score? Remember, they're inversely related. So I'm expecting my z-score to actually go down. Let's see if that happens. Pause and try to calculate the z-score yourself. Okay, so hopefully you came out with 1.45. If you didn't get that, take a look at it, pause the video, and check your calculation. The only thing that changed in the calculation was where my p-hat was, because we changed the p-hat. So we go from having evidence, both provide evidence up here when we have 7 out of 8. Now, if we look at this and we look back at our tables, this provides both of these. So we already discussed this, the 7 out of 8. I want to look specifically at a 6 out of 8 correct. They both provide no evidence against just guessing. So there is no support of the alternate hypothesis here. Remember, once again, though, we cannot find evidence for the null hypothesis. We can just find evidence against it. So changes in p-hat. So therefore, changes in p-hat affect our p-value and our z-score. So we're looking at things that can affect the p-value z-score. Let's at this time suppose that she'd been asked 16 questions and, let's try and, sorry about that, she picked the correct answer 14 times. How would that change our p-score? P-score, where am I getting p-score? P-value and z-score. Let's investigate using the one proportion applet. What I would like you to do is try this on your own and then come back and compare your answer to mine. You do not have to print this out. I just want you to look at it and see and make sure you see where everything is going and coming from. So I had run these applets. I had run the applet and used, once again, everything's pretty much the same. You're going to notice, though, that now we're looking at the number of tosses being 16. And I started, here you see the count, and I just wanted to show you when I hit click, I started with, it always starts with number of heads, at least on my machine, and then I clicked on proportion of heads. So this 14 would change automatically to 0.875. So I just printed it midway through so you could see it in case you haven't had luck with the applets working yet. So it says the proportion of repetitions here is 0 out of 1,000. So they didn't count any that were up here. Now, is the probability 0 that that could happen? Actually, no. We don't say that it's 0 because there is a possibility that it can happen. So whenever we see this count of 0, what we do is we say that the probability is not exactly 0, but it's very small. We're going to say 0.001. All right, so that's going to be our p-value when it says 0. Just because it wasn't observed doesn't mean it's impossible, but it means it's very, very unlikely. So if you convert this to a percentage, move it over twice, you'd get 0.1% of the time. So very, very unusual. On the other hand, with this tosses at 8, this one I printed after, so you can see that. There is more evidence, there's not more evidence, excuse me, there are more observations here we see. So our p-value in this case is 0.0280. So what does that tell us without thinking much about it? If you, well, with thinking a little bit about it, have a larger sample, does it make sense that you would get better data in general, assuming it's a good sample that you're pulling? You would get better results? Yeah, it makes sense. Think about it long term. If you flip a coin, let's say twice, and it's both heads, or it's both, let's say both tails. So the probability of getting heads is 0. Does that make sense? No, not really. That was only 2 flips. Now, if we did 10 flips, the odds of getting 10 tails in a row is pretty low, right? Now, if we do 1,000 flips, once again, we're going to start seeing that center of 0.5, all right? So if you haven't, pause now, and this is the one box you could not have filled in because it's a little different. So with 14 correct instead of 7 correct, our sample size went from 8 to 16. Our p-hats do not change. Our simulation-based p-value, once again, we don't say it's 0, we say it's approximately 0.01, and our z-score went up. So this provides much stronger evidence that Sarah does better than just guessing. So a bigger sample size gives us more, can give us a stronger result. Now, stronger evidence. That being said, can we just go to infinity? No, there's definitely, you don't want to choose more than 5%, because after that, it's almost not a sample. It's almost, you don't want to talk to everyone. You want to talk to some. So it doesn't go on forever, but as a general rule, a larger sample size will give you a better result. I'm going to write that down and pause your recording, do it, and then we'll move on. So in general, if your p-hat is staying the same, so we're looking at the proportion, you notice that that did not change. If it stays the same, the p-value and z-score changes if n changes. You have stronger evidence with a larger sample size. But if you take a smaller sample size, you're probably going to have weaker evidence. Now, we're going to switch gears a little bit. We're going to talk about, it's a new idea here, a normal approximation-based p-value. Most of us have heard about the normal distribution. It can also be called, and don't flip out, it's the Gaussian distribution. If you have not heard of these, that's okay. Some of you may have. It's also called the bell curve. You know, you hear about, oh, are you going to, when people say, are you going to grade on a curve? They're talking about the bell curve or the normal. When the null distribution can be approximated with a symmetric bell-shaped curve, we can describe the overall shape of the null distribution as a normal distribution. Well, one of the benefits of that, and you're like, well, what are the benefits? As you can see here. Here is what we've been doing. We've been generating these null distributions. Now, if you can see that where it's now grayed in, That's with the bell curve kind of laid over it. So it's showing roughly what it looks like, what the distribution looks like if it was all under within a bell curve. Why do we care? Why is it important? Well, when the null distribution could be described as a normal distribution, the p-value can be found by finding the area under this curve. So you can see there's a curve here. And in calculus, integration is how we find areas under curves. Don't panic. You don't need calculus in this class. We're not going to do it that way. But I just want you to be aware that we can find the area under the curve, which is going to give us another way to find the p-value versus doing simulation. We can just assume it's a normal distribution, and then we can calculate the p-value. So you're like, well, how am I going to do it though? I'm not doing integration. Well, the one nice thing is the one proportion applet has a normal approximation button. So that's important. So make sure when you're on there, you're going to notice it a lot of times. It showed up over here. So when I count the actual proportion, so this is based on the count, you get 0.42. 0.042, excuse me, as the p-value. Now, when I do the normal approximation, in other words, it is finding the area under this curve here, it found a p-value of 0.034. So all I had to do was click this box and up it came. So once again, this is based on counts. This is based on the area under the curve. And it gives us the curve approximation. So instead of having to do counts and run simulations. Are these numbers pretty close? Actually, they are. They're not that far off, not even 100th off. So they're pretty close values. The nice thing is that means you don't necessarily have to run a simulation to get a p-value. So note, the simulation-based and normal approximation-based p-values are not exactly the same, but that's okay. They're close. Normal approximation is valid to use. Now that's key. It has to be valid to use. We can only use the normal approximation, in other words, push that button and get something meaningful. To use it, certain conditions must be met. The normal approximation is valid is when the sample is large enough. And you're like, well, what's large enough? I mean, large enough. Are we talking 10, 1,000, a million? Well, the loose rule that we're going to use is there's at least 10 successes and at least 10 failures. So 10 heads, 10 tails. All right. When in doubt, if you're in doubt, if it doesn't look like, let's say you had, would it work if I had 100 successes and 1 failure? Could I use the normal approximation? No, you couldn't, because it failed. Yes, it has a lot more than 10 successes, but it only has 1 failure. All right. When in doubt, use the simulation-based p-value. So each of these charts below are screenshots of the null distribution for 3 different studies. A here is the Sarah study, and you see some detail about each of these below. B, this is one we didn't do, but it's about psychic functioning. It's tight, it's a little bit tighter. And then C is the one we've been doing all the way along, the advantage red. So when I'm looking at this, I want to know, can I use the normal distribution? Take a second and see which one, circle the ones that you think you can use the normal distribution for, and seeing if you can come up with why that would work. So looking at A, Sarah, we only had 8 total in the sample. We know that there were 7 successes and 1 failure. We don't have 10 on anything. We can say right away, no, that this one doesn't work. Well, you'll notice that there's huge gaps here in between each one. Remember, when we find the area under the curve, it's the whole thing filled in. You can see right away that it just doesn't even make sense. B would be hard to do on your own. And I should have given you a little more information before I asked you to do that on your own. I apologize. I should have told you at least that the number of successes was 33. Okay, so the number um, of heads was 33. So then we know the number of failures was the 97 because that's the sample size minus 33, which gives us 64. So are they both greater than 10? Yes, so we can use the normal approximation for that. C, it's pretty obvious. You can just see by looking, we can use it. Look how densely filled in. And it's densely filled in under the curve, densely filled in, and it's not funky skewed. And we're going to talk more about skewed in a bit, so don't worry too much about that. But it's not, it's a nice, pretty bell shape. It's not funky on one end or the other. So the larger the sample size, we notice the less gaps they're in, and under the curve is more filled in. Remember, we're finding area under the curve, so the more filled in, the better, the more appropriate it is to use the normal approximation. But remember, in general, we need at least 10 successes and 10 failures. Now, you're like, oh my gosh, I'm starting to lose my mind. I know, I understand. Let's take a moment and review, take a breath, take a drink, review of the tests of significance. This is the review of the last couple days. So we use tests of significance. Our hypothesis tests are used, so this is general review, to assess the strength of the evidence provided by the data from, always we're talking about well-designed studies, against the random chance explanation, and we find support, hopefully in support of our research conjecture. In other words, our H sub A. Okay, so we're looking for support for our alternate hypothesis. Strength of evidence can be quantified. In other words, we can come up with a number for it using the p-value. We can do it using simulation, which we've done by generating that null distribution, and then looking to see how we did by putting in the value of our p-hat. Because remember, at this point, we're not talking about means, we're strictly talking about proportions. It also can be calculated using mathematical theory, which relies on the sample size being large enough. Remember the 10-10. 10 successes, 10 failures at least. And that's called the normal approximation based value for your p-value, not p, just p, not just p-value. And or you can use a standardized statistic. Should your p-value and your standardized statistic give you the same, help you to draw the same conclusion? Yes, it should. If they don't agree, you may have made a calculation error. So that's always a good way to check yourself. Now remember, when we, in statistics, we need to state a conclusion, interpret our results. You can't just state a number unless it just asks on an exam, just like, give me the z-value. Well, you give the z-value, fine. You don't need to give anything else. However, if I ask you to state a conclusion, and we'll come up with some more summaries so you can see that, not just conclusions, but ways to word them and how to know to do it appropriately. You just can't give a number, because remember, in statistics, we're really looking at research questions and whether we have answered them, or we want to give our answer, I should say, in a way that's meaningful. That's it. Day 5 lecture. I hope you are doing well, and that's it.